Thank you for this opportunity. So I guess you all hear about, the impressive success story of the use of multi-precision algorithms to reduce the computation time of some application up to a factor of 4, saving energy, but without compromising on the accuracy. Those stories are nice, but so far, all those nice and success stories are about dense matrices. So the natural question that comes to mind is, what about sparse matrix computation? Can we use the same multi-precision algorithm for sparse matrix computation for memory-bound kernel? So those are the questions that I really want to address in this talk. It's more about questioning. It's not working. Okay, let's do it this way. Something's broken. Okay. Thank you. So let's start with the question that I want to address here. So the first question is, I have an application or a kernel. If I run it or execute it on double precision and then execute it again in single precision, let's assume that I'm okay with the single precision accuracy. Can you guarantee or can you see with certainty that the single precision version will run faster than the double precision one? That's my first question. And the second question is more about sparse direct methods. And can you say that, for example, the nice algorithm that we are using for iterative refinement can also work when I'm using a sparse direct solver? And the third question is mainly about sparse iterative method for solving linear system of equations. Those methods are mainly dominated by sparse matrix vector product and also by preconditioning at each iteration. So if I want to perform a few SPMV or the application of the preconditioner in lower precision, can I have any gain? Is there any speed up doing that? If yes, any idea about the speed up? If no, why? Maybe I hope that by the end of this talk, we can have some insight on this question. Maybe we can be surprised. I hope. So before moving and addressing those questions, I simply want to mention the two main classes where lower precision or multi-precision algorithms can be used. The first is basically all the application where higher precision doesn't matter. And the first that comes to mind is simply deep learning. And we have a very nice result there. But not only, you have many scientific applications where we don't really care about computing, for example, loose approximation with 16-bit digit accuracy. Or in many, for example, iterative multi-precision, multi-level algorithm for the first step where all the computation are caused, you can simply use lower precision. If you are solving some approximate solution, it doesn't make sense to solve it accurately because you are solving a wrong problem anyway. So an approximate solution should be fine. So the second category or the second class of problem that we have here are the application where you really care about high precision, but those applications have some inherent process where they can accept any initial solution and then improve it. And the basic, example here is the iterative refinement algorithm, where, for example, you can simply compute the most expensive operation using single precision, and you keep operation, then you go down and you refine it with a few high precision and costly operation, and at the end, you have a good solution. In this example, you have the two versions, but recently, as we see in few presentations, Nick Hyam and Carson have proposed the three precision variant, and we have Hazam and the Jack Dongara team who implemented this algorithm for X speed up, and the success story continues with QR factorization, Cholesky factorization. So far, we are good. But I want to see numbers for sparse linear algebra. That's what this talk is about. In 2008, some times ago, the team of Professor Dongara with Alfredo Buttari, they've done some nice work using, some sparse solver like SPLU and MEMS, where they implemented the iterative refinement algorithm, but in that case, they'll be using a sequential version of those code. That means all the execution have been done using a single process. And they are not to be blamed for this, because at that moment, the SPLU, parallel version, doesn't have a single precision variant. So the only way you can go with those multi-precision algorithms is simply using the sequential version. So today, one should take those algorithms again and then use the modern architecture and use the parallel version. Because if you think about multi-precision, the main reason why we're doing it is for performance. So if I have a faulty core architecture, it's better for me to have a parallel code than simply use a sequential code and then use, lower precision. And the second part will be assessing this work in the context of, sparse iterative solvers, as I said before, checking if I have any gain by running low precision SPMV, application of a preconditional, and so on. So to do this work, we got a selection of 42 matrices from the Tim Davis collection. Why 42? I don't know. If you have more matrices, I'll be happy to get them and then add them to the benchmark. But 42 looks to be a good number for me. And those matrices are from a wide range of applications, and the size vary, and they cover a nice range of from like 500,000 to 27 million non-zero. And for the sparse direct solver here, you have SPLU empty, which is threaded version, MKL Paradiso, MEMS, and ANFPAC. So during this work, I've been surprised that there's not a single precision version of ANFPAC. I can trust that, but this morning I had a chat with Tim Davis, and he confirmed that he doesn't have it for some reason. And for the preconditional point of view on GPU, I'm using CoSparse, incomplete LU factorization, and for the SPMV here, I'm using MKL. Also, I'm using the CoSparse SPMV, and for both benchmark, I'm using the CRSAR format. And from hardware point of view, we have a nice collection of hardware. Good. So this is the first result that I want to show. I'm using here Paradiso, and what is happening here, I simply get a matrix and perform an LU factorization of that matrix in double precision. I'm not solving yet, and then perform again an LU factorization in single precision. I simply want to see the speed up I'm getting from it. No solve, only factorization. No iterative refinement. And what I'm expecting here is it to speed up. So I'm showing the speed up here, the higher, the better. I want those red bars to be as high as possible. And the benchmark is on the Intel Skylake with 40 cores. So when I run first this benchmark, I've been surprised myself, mainly because most of, the performance gain are for at least 3 or 4 matrices, and for like 62% of the case, there's not any gain at all. And that's not the most surprising part. The most surprising part is it happened that for 30% of the case, going lower precision lead to some performance loss. That's a bit troubling. I thought there was some issue with the MKL Paradiso, because it's quite hard to understand that. So before doing any profiling to understand what's happening, maybe the double precision version is highly tuned and the single precision version is not. I tried the same benchmark with MEMS. And the result doesn't change that much. It's again the same, observation. Like for more than 50% of the case, there's not any performance gain at all. Why? Where is this coming from? I'm expecting the lower precision algorithm to give me 2x speed up for sparse linear algebra, because they may be compute bound and memory bound, both combined, lower precision should help. Then we move further with SPLU empty. Here the story started very nice because you have more matrices giving close to, more than 1.2x speed up, but you don't have to resolve for all the matrices because PLUMT was running out of memory. I tried many filling factors to solve this issue, but the problem was still there. So I assume that this may be my own ignorance, that I'm not able to set up the parameter very well, but I discovered a few people who also had the same issue with PLUMT. So I just presented the result of three mail solvers used in the community, and I can see that for all of them, for more than 50% of the case, I cannot see any performance gain. That's only for the factorization. And if I want to go further for the refinement, I'm going to lose more performance. And what about, for example, the preconditioning for example, incomplete LU factorization on a GPU? Those results are for, NVIDIA V100 GPU, and it's even worse in the sense that, for the CPU version, I was able to get something above 1.5 speed up, but here, I'm not able to gain anything beyond 1.5x speed up, and 1.5 is something like you're simply getting 30% on your time reduction. So it's quite, surprising for me. But if you think carefully about it, it shouldn't be that surprising, right? Because one main component in this benchmark is that if you think about density linear algebra, you take your matrix and you factorize it. Everything is about floating point computation, and you're happy. But for sparse linear algebra, you have a big part of your computation is about reordering the matrix to, minimize filling and analyze phase of your, factorization. And those phase of analyze and reorderings doesn't depend on the precision. So if you're using, low precision, half, single, or not, you are not able to reduce those time. But not only, it's not the only reason why we are not observing that, 2x speed up, because if you return back for more than, 50%, we don't have any gain. That means even if I have a very good analyze and reordering phase, I won't still be getting anything because not having 1x speed, that means even the factorization, the numeric factorization step is cost me the same thing both in single and in double. That's what it means. So maybe you're wondering if I have the same observation using the AMD or the, GPU, P100 GPU. Yes, the results are the same. I have them. If you want to see them, I can show them to you. And the same thing on the Intel as well. So the question is, now, let's assume you already have the factorization and you want to use it in your precondition as a preconditioner in, iterative method. Will it be meaningful to solve or to apply the precondition in lower precision? I'm talking here about the backward and forward substitution. Can I have any gain at all doing that? And that's the question that I'm addressing by this curve, starting again with Paradiso. So here I consider that I have a gain when the speedup is above 1.5x, because those are not the more time consuming. So anything below 1.5x, I assume that I don't have any gain. So here, the story is a bit promising because for few matrices, I can have something above 1.5. It looks a bit better than the factorization, but still it's not what we are expecting. And the same thing happened for MERMS solve as well, and for super LUMT and Q-sparse. It's almost the same story again, but the result is a bit worse for the GPU version, and we will explain why. So basically, if we take the solve algorithm, what it's doing is a backward and forward and back substitution. The problem is not really about the latency or about computation. Those algorithms naturally don't have enough parallelism. So if I give you some algorithm that's not able to use the bandwidth properly, is not able to use the number of core you have properly, going lower precision is not going to help you. Because the main thing that going lower precision is going to do for you is to, give you a better bandwidth or using better the computing resources. So if you are not able to explore them by your algorithm in higher precision, going lower precision is not going to provide any gain. And the second point is for a practical point of view. If you have a look on the new algorithms that we are designed for multi-precision, they require, for example, if factorization can happen in half precision or single precision, then you want to apply the preconditional in double precision. That means you need a way, after your factorization single precision, to apply it in double precision. But in most of the solvers that we have today, for sparse linear algebra point of view, the factor L and U of the factorization are stored in opaque format. What it means is that you don't have any way, when you are using Paradiso or MERMS or SuperLU, to be able to factorize in single precision and apply in double precision. Those are some practical issues. So you'll be limited at simply applying the preconditional in the precision of the factorization. That's some high limitation. So I want to point this out. Maybe the community can work better in other implementation when they can provide a way of mixed-precision solver where you can still apply factorize in lower and apply in higher precision. So the last question here is about SPMV, the most dominated part of iterative solver. So if we are able to do anything about SPMV, then we have a hope to improve, the iterative algorithms like GMRS and conjugate using mixed precision. So the result here. So basically, it's the same scenario again. No refinement, nothing fancy. You simply perform your SPMV in double precision, and then you perform it in single precision, and you measure the speed up. So the first curve on the top are mainly about CPU execution. They are quite promising. Like for more than half of the execution, you have some speed up that's above 1.5x. While on the GPU, it's a bit surprising that you are not able to gain, over 1.5x speed up. And that's a reason for that. So the main conclusion that we can get from this, plot is if you have in mind of using mixed precision iterative method, maybe you can keep yourself on a CPU than going to a GPU, unless you have some very nice algorithm or technique of latency hiding on your GPU. Because the main reason why you are not able to see a very good speed up on the GPU is for the latency, because the SPMV is merely a latency bound kernel. But on a CPU, we can still see some speed up because the CPU have a very large caches and that's prefetching strategies that help somehow to hide the latency better compared to the GPU implementation. And the second point here is about the data conversion. When you think about SPMV, you simply take your matrix, double precision, you convert it, and you apply the multiplication in single precision. But the conversion itself is as well memory bound because it's simply a copy. So if you want to perform a conversion, then SPMV, that can be a bit expensive. So something that can be done, maybe we can, in the community, implement some mixed precision version of SPMV where you can still take the matrix in double precision, but perform the conversion on fly to apply the SPMV in lower precision. But performing the conversion, then the SPMV can be a bit time consuming. I measure the time on both GPU and CPU. They are not that cheap compared to the cost of one SPMV. And another point is, in most of the iterative solver, you really want to keep your memory consumption down. You don't want to have a very high memory consumption in iterative solver. And one point of most of those, mixed precision algorithms is that you have to hold many copies of your matrix. So another way going around this issue is again have those fuse kernel where you don't have to take the matrix and convert it completely from double to single or from double to half, but on the fly you want to perform your conversion. So if you, for example, want to operate on the first row, it will be converted, at real time, and apply the operator, and you have to move on. Those are a few tricks that we can use to, solve the memory footprint issue. And currently, I'm working on the matrix-free SPMV. That's something that, because in many applications, for example, we don't really have the full matrix, but we can still take advantage of the operator and do it in lower precision. So my final takeaway for this talk is that, we've observed a very nice result of iterative refinement algorithm, but they are for dense linear algebra. And for all the benchmarks that I've done for, sparse direct solver, I'm not able to see those speed up. And a very wise friend of mine said something yesterday that I want to share with you. He said, Mawussi, maybe the problem is not about the method itself. Maybe the problem has to do with the solver that you're testing. Maybe the solver that you have today for sparse linear algebra, they are all not good in the sense that for mixed precision, in the sense that they still have a very high cost for, the analysis phase that is still sequential. That's still sequential. And the second point is maybe those solvers are not able to exploit, lower precision efficiently. And I hope that in the future we'll have a new generation of solver for sparse linear algebra that can exploit those costs, those opportunities and have low gain. And the other point are what I've just said. Also for sparse linear algebra, we are not really able to exploit the new unit like tensor core and TPU efficiently because they are simply doing dense multiplication, and sparse linear algebra is not really fully about dense. The dense opportunity are few, or the matrix or the cluster are not that big to exploit the tensor core efficiently. And my last point is, it's a lesson that I've learned myself, is if you want to jump in the jungle of multi-precision computation, take a time and ask yourself, you have some bandwidth, measure it for your application. Are you able to use the bandwidth that you have already? If you are not able to use it, if you have a bandwidth, you are not able to achieve even, 60%, and your application is bandwidth bound, don't use lower precisions. It's not going to help you. You have also to measure, the peak performance of your code, of your kernel. If you are not able to get up to, 50% of the peak performance, don't go lower precision. It's not going to help you. So those are my takeaway. And thank you for your attention. Working for NAG, and this work, has a few partners like Professor Dongara, Nick Hayam, Françoise, and from NAG, my line manager, Craig Lucas, and Mike Dewa on the back. Thank you for your attention.